Our first speaker will be Moshe Mishali, the CTO and co-founder of Deep AI. So a little bio on Moshe. Prior to founding Deep AI, he was an algorithm architect at EasyChip. His prior experience includes consulting on hardware and software. And he spent 6 years in the elite technology unit of the Israeli Defense Forces. And he has a PhD from Technion. So welcome, Moshe, and you can go ahead and share your screen now.
So my name is Moshe Mishali, and I'm a CTO at DeepAI. And actually, I just heard the keynote by Linley, and I think this session is very aligned with the message of from the cloud to the edge. So we will touch on many points that were mentioned in the keynotes. My talk today is about commercializing AI, and we will describe a kind of a paradigm shift in how to deploy AI models in order to enable the full cycle of both the training and the inference to run on a single commodity hardware. Commodity hardware that you can put on edge locations. And as a result, we can reach robust and self-contained commercial applications. So I will explain more in the coming slides. So in today, deep learning, and we also saw it in the keynote, there is quite a distinction between what is being done on the data center and what is being done on the edge. For training, we use the data center where we have powerful GPUs, V100 and Ampere, which have many floating point multiply accumulates that they can deliver. And typically the training is done on dense weights, or in some cases on some kind of structural sparsity during the training. But once the training is completed, data scientists need their expertise in order to convert those floating point weights into int8 representation that is typically used for inference. Most of the time, we also reduce the footprint of the model using pruning techniques. So eventually, a very small footprint can be used for inference, and this can run on, as you saw, on CPUs or small GPUs, FPGAs, etc. And the question that we are asking and we study in this talk, can we train at the source? Can we do all the operations that we need to do directly where the data is being generated? In other words, at the inference location, directly using int8 operations without going to some data center which can be far away. Just do all the operation directly on the sparse weights using only int8 operation. And the driving forces towards the edge are many, and you saw most of them listed in the keynote. Among them are security and lower latency, and you don't need to pay for the traffic outside your organization. Besides, reliability and privacy. And I think one of the key advantages that drives everything to the edge is that you can personalize your models. So if you have different edge deployments, and you can train each one of them to the personal properties of that edge location. So you can imagine that eventually we will have personalized training running on our mobile devices that can give us the best user experience that we can get from our device. And the paradigm shift that I was talking about is, instead of doing the inference on the edge and then transfer all the data that was collected to one central location, can be on the cloud or some huge data center to do the training, DeepAI provides a solution to do both the inference and the training directly on the edge. So most of the time, the common practice would be to do cycles between inference and retraining on the edge. Occasionally, or quite rarely, we will go to some central location to combine results between all those edge locations. But the common practice and the everyday use would be to stay on the edge without leaving the platform that you are running the inference and the training. Now, what are the challenges and what are the developments that we have prepared in order to be able to run on the edge? So first of all, and I think this was also mentioned in the keynote, floating point is considered essential for training today. All the methods that were mentioned are using floating point in some variations of it in order to do training, but inference is typically done on int8 in fixed point. So we have developed quantized training at 8-bit fixed point that can run end-to-end with this resolution, and by that we can connect directly from the training to the inference. And of course, besides all the efficiency aspects of doing training at a lower resolution. In addition, when we are working on the edge, most of the time, as I mentioned, the models are sparse, they are smaller, and what we provide is a training that can run and can adapt to the sparsity patterns, and during training convince the system to select what are the parameters of interest and of importance for that training session. So we are not talking here about post-training pruning, but on adaptive sparsity training that is done while the system is converging to the solution. Together, those ingredients can take us into two different locations. If we will take those to an ASIC that is targeted to the edge, then we can reach about 100x in efficiency with respect to existing ASICs that are doing today training. But our go-to-market strategy and our validation of our technology is to use FPGAs. So our product today is using FPGAs, which, as you know, are manufactured by large companies like Xilinx and Intel. And those FPGAs feature many int8 multiply accumulators and programmable logic that we use for our algorithms. So all in all, we can reach with existing devices without investing in a new hardware. We can reach around 10x gain in performance right now, already available today. But as I mentioned, if we will push this technology to ASIC or to be embedded together with a larger SoC, then we can reach a much higher performance gain because of the dramatic improvement of the 8-bit fixed point and also the sparsity. Our vision is, and this is what we provide today, is an integrated and efficient training inference. Most of this talk about edge, but ultimately it can go across the board to the data center and ultimately to the on-device implementation. And everything is done with high performance without losing accuracy, so that we can benefit from low power and low cost AI hardware. So I would like to better define what we mean by commercial AI workloads. The AI domain consists of many types of application and many type of tasks that are being carried out, and some of them are research type of workloads. So for example, searching for new architecture and developing new network models. And this is something that is done mainly by academia and hyperscale. And this is clearly where the training on cloud on massive amount of cluster of GPUs is needed. But on the edge, the commercial applications are typically not interested in developing new architecture, but using the existing one. So for example, it was mentioned ResNet, and you can see in detection YOLO and SSD and other known models of networks that are already used and already proven themselves. So for edge and for commercial AI workloads, what we mean is the standard cycle between doing inference with these networks, and from time to time, we train them based on examples or new examples that we received, and we want to improve their accuracy. And this is what we want, this is what we provide, this integration between training and inference on the edge for this type of application, commercial type of applications. So I would like to spend a few slides about the challenges and how we solve them when we go to edge AI training. Of course, training at the edge is something that is not done today. And I mentioned two key ingredients, int8 and also sparsity. And they bring into the game a lot of challenges. The most important one is not to lose accuracy. So we go into a lower precision, but we still want to maintain the same accuracy level of the floating point, as if we were training on a data center with a GPU with a floating point operation. Another aspect, another challenge is that we don't have access to the dense set of weights. The model was already reduced, some of the weight were pruned, and we need to keep training this model without increasing the sparsity. So we need to handle the sparsity that exists, and I would even add more on top of that. We would like to handle unstructured sparsity. You saw in the keynote that Linley mentioned that today there are some attempts to do structure sparsity in order to gain around factor of 2 in speed up. What we are talking here is unstructured sparsity that can bring x10 in performance using unstructured and unconstrained sparsity. Another aspect, another challenge for edge applications is that they need to run seamlessly between those inference and training modes. And there is a great statement that I found that AI needs humans on the loop, need to control what is going on in this framework, but we don't want the data scientists to come every time, but we need to switch between training and inference. So we need to make everything transparent, everything automatically, and this is another challenge that we need to address. And I would like to now to expand on each of these challenges. I will start with the int8. There is a reason that a floating point is used for training. Backpropagation, which is the massive computation part of training, compute gradients. Some of them are small, some of them are large, and they are trying to push the system, to push the network towards some global or local minima. int8 has only very limited dynamic range, only 256 values. So of course, it's a very limiting factor in training. What we have developed at DeepAI is a kind of dynamic range matching or dynamic range control that runs along the system. So while all the multiplications are done at 8 bits, there is an assisting control logic that resides in each layer and also between layers in order to effectively expose a much higher dynamic range. So the essence is that the multiplications are done at 8-bit, and this is the area that you will spend in silicon, but some extra area, small ones, is needed in order to compensate for the dynamic range of the int8. For sparsity, as I mentioned, I will focus on a convolution, which is a popular, most popular function that we need to implement, or kind of dot product. It's very easy to have convolution or sparsify the convolution along specific dimension like channels or filters. And the multi-core architecture that is popular today also require you to have some structure in the sparsity. So only some of the channel or some of the filters exist. But this is not what the network would like to have. So for example, some of the features, you can imagine that we will require a lot of parameters in order to capture them, and others may be more simpler. So with deep AI hardware, our algorithms enable fine-grained sparsity. By that we mean arbitrary, unstructured sparsity. We give all the freedom, all the degrees of freedom to the network to select which parameters are needed, and we exploit those decisions of the network in order to speed up the training by doing only those non-zero multiplication, even if they are not aligned with some dimension of the nested loop here. From the operational point of view, as I said, we need a mechanism to switch again and again between inference and training. And here, the fact that we are working at int8, and the training in some sense is inference ready. We don't need to do any quantization and any pruning once we finish the training, so it can be directly connected to the inference. And we can envision some situation where the system during the day hours is working in inference mode. And once there is some idle time or off hours, the system is switched by switching a bit stream or just switching the mode of the FPGA or the ASIC into a training mode. And then the examples that were collected during the day are used to improve the accuracy of the system. And again, once the system goes to production, we are immediately ready and we don't need to have any human in that loop. Of course, from time to time or at low rate, we will have some monitoring and some metrics that everything goes okay, but the everyday work would be fully automated. Trying to summarize what you've seen so far, the x-axis on this drawing is the model size and the y-axis is the performance. And most of the attention today is given to large models like, imaging task, which requires very deep network and a very large set of parameters. And over here, we said that using sparsity and int8, we can reach about 100x. But there is a large amount of segments in that area, manufacturing, robotics, antenna, etc., where the model is small. And over there, you can't really use multi-cores. They are not efficient in that regime. And here, once again, the fact that you can use int8 and optimize design on FPGAs, for example, can give you a much higher, even much higher than 100x performance boost. Let me, okay, just one more slide before numbers. Our solution integrates into existing frameworks. So from the data scientist point of view, they keep working on their Python, familiar Python environment like TensorFlow, PyTorch, etc. And under the hood, our compiler stack will take the network and optimize and select the appropriate bit stream for the FPGA. And in this setup, we can reach about 10x gain in performance per power or per cost. Let me show you some numbers. Over here, we can see classification tasks, several data sets. Some of them are public, some of them are proprietary. And you can see comparison in number of epochs and training accuracy between an int8 technology and the equivalent floating point. We use the same hyperparameters and same learning schedule, so we didn't added any data science to these results. They're using the same code for training on both sides of the slide. So this is for classification, and you can also see that the same goes for detection. Over here, it's a tiny yellow v3. Once again, data sets, and you can see that we reach almost or nearly the same accuracy with int8 technology. Going to performance and costs, what we show in this slide is that using an Alveo U50 card, which is a 75-watt PCIe card by Xilinx, we can reach on Resident 50 ImageNet, standard benchmark, we can reach 800 images per second throughput, while on V100 GPU, which is a data center grade GPU, we can reach 360, so more than 2x in speed. And if you normalize the speed to the power or to the cost of such a device, you can see that we are approaching the 10x gain that I discussed before. And I think we also need to add on top of that the fact that the server cost for small devices is much cheaper than if you have to build a server to host data center grade devices. So with that, I will summarize. What we provide is an option and the solution to do edge training for application that you need to do inference, and from time to time need incremental updates to your model. Everything is done in int8, so it's a direct connection between the two tasks, and we keep the sparsity, and we also use it during training and inference in order to speed up the performance. Everything is done on commercial FPGAs, standard ones with low power, low cost, with minimal efforts from the data scientists in order to adapt this solution. So I would like to thank you for joining me, and just a minute. And
thanks, Moshe. Could you go ahead and turn off your screen sharing, and we'll go to the Q&A.
Mm-hmm.
Great, thank you. So it's very interesting talk. It's good to see some work on-device training
Mhm.
to complement the trend that we see towards on-device inference. Um, I have some questions to start with. Are you providing the hardware IP as well as the software? Could you tell us a little bit more about how you engage with the customers?
Yeah,
Do you give them the RTL to compile on the FPGA, or do you do that? How does that work?
yeah. So maybe just I would share the screen once again for this question. Let me share the screen. This is a slide that regards referred to your question. We give everything in this dashed box to the customer, meaning that we give all the software stack and all the bit stream that we have developed. And from the customer point of view, they keep working on the TensorFlow or on the framework level. They don't see really the RTL or the Verilog. They simply need to run their network on the standard framework. And simply, it's a matter of one line of code to change from importing like Keras to importing deep AI libraries. And under the hood, all the magic occurs. So under the hood, we take the network and convert it and optimize it and eventually select a bit stream. But the data scientists need to know nothing about FPGAs.
So you could go ahead and turn that off. Is the starting point then really a pre-trained model, or do you just start from raw network architecture?
Yeah. So it's a nice question. Basically, we have developed our technology in order to do training from scratch. So we can, as I said in the beginning, we can compete with all the way from data center to on device at the other end. But we think most of the benefit from our technology is for the edge, where you already start from a pre-trained model.
Mm,
And from there, you keep going on and improve your model again and again on an everyday basis, regular basis.
okay, so incremental retraining.
Yes.
Okay, I'll go ahead and take some. I see some questions coming in from the audience.
Mhm.
Um, the first question we had was you talked about the advantages of an FPGA versus an ASIC. Um, could you say what accounts for the 10x, sorry, difference? You said that an FPGA is 10x faster, but an ASIC could get another 10x on top of that. What is the difference between the two?
Yeah, of course. FPGA has less density in transistors than you can put on an ASIC, and basically our technology we have developed it to replace the every of the multiplier in your design. So on FPGA we are limited to the structure of the FPGA and what we can put inside. But if we will take this to an ASIC and we will design our custom ASIC to use our technology, then of course you will get the boost that you will get in any other domain when moving from FPGA to an ASIC. Yes, it's around the same performance boost that you will get in every other domain.
Mm-hmm.
Okay, I think most of the performance boost is due to the fact that int8 multiplier are much more efficient, much more dense in area when floating point ones.
Sure. What do you see as the bottleneck for the training or the retraining? You need to feed the new weight data in. Is it the memory bandwidth, or what would you say is the major issue there?
Yeah, I think, as I said, we are doing some kind of balance between sparsity and training and incorporate between them. So as we go and sparsify the model, there are less weights to bring from the memory, but the activation and gradients do not change in volume. So we still need to keep feeding in the system with the same volume of information for the training. Just the portion of the weights goes down as we sparsify the model.
Mm-hmm.
Today, we see quite a balance between our compute speed up and our memory bandwidth that we run on. U50, by the way, has the HBM on device.
Okay. Okay. Another audience question was how you do verification from how do you verify the unstructured sparsity is correct during training?
Yeah, so for correctness, we run inference and we see that we get the same validation accuracy as we saw during training. I'm trying to understand what was the subtext of this question. Clearly, for the data scientist, it doesn't really matter what solution would the network will eventually find. You know, you can find many solutions to the same problem as long as they work and bring in the right validation accuracy.
Right, right, right. It's maybe not so much correctness as acceptable accuracy.
Yeah, accepted.
Question on whether DeepAI is using the Xilinx XRT.
Yes, the answer is yes.
Okay.
We build on top of what Xilinx can bring to the market. They give all the runtime libraries, and on top of that, we bring our software stack.
Okay. And then do you support tiny ML models?
Yeah, as I mentioned in the talk, there is a large regime of model sizes, starting from ImageNet and ResNet 50 over ImageNet, etc. And there are, on the other side, other extreme small models that are used in manufacturing and are used in robotics, etc. And we also bring a lot of value in this regime.
Okay. Another question on basically the go-to-market, how you engage with customers. Are you interested in engaging with non-FPGA customers at this point? Or is this strictly
it can be very interesting question. We have a lot of discussions around this point with partners and customers, and it would be great to hear more from the audience if they want to.
So they can contact you again later on in the breakout session.
Yeah.
Great. Have a couple more minutes. I had some more questions. Please go ahead and enter some if you have them as well. So I guess question on how you achieve sparsity. I think you said that you're not doing the pruning. Could you explain a little bit more about your secret sauce?
Yeah, I can say that what we are actually doing is we are using the system, using the neural network itself to tell us which portion of the weight, which subset of the weight is important. So we are not deciding on pruning based on some, coarse metrics that we can invent. We are using metrics from the neural network itself, and we are convincing it to use only subset of the parameters. So you can imagine that during training, gradually the sparsity reach a very good level.
Yeah. Right. And then I guess the next question was, do you use any floating point at all? Or it's strictly int8?
No, strictly int8. All the multiplication are int8.
Great. Well, I'm afraid we're out of time. That was a great talk, Moshe. We'll see you in the breakout sessions later on.
Thank you.
Thank you very much.